Hello and welcome to this next lecture on fundamentals of acoustics. In the last class we saw the transient response due to initial conditions inside a rigid walled rectangular box, rigid walled rectangular box. Okay. So now today we will look at the steady state response of the interior of a rigid wall box due to a harmonic source, due to a harmonic volume velocity source, volume velocity source. Okay. So once harmonic comes, we are talking of Helmholtz equation. Okay. And once steady state comes, that means we are not interested in the initial condition response, it has decayed. Okay. And as far as boundary conditions are concerned, the walls are rigid. Okay. So we know the mode shapes from previous lecture. So now if I write the equation for this situation, del square plus k square, the pressure is equal to minus a q, okay, where this q can be expanded as minus I omega rho q volume plus a del dot f. Okay. So this is the monopole type source and this is the dipole type source. Okay. So at this point, that is not important for us, we will club it under Q and it is harmonic. Okay. And Q volume here has volume or unit volume per unit time units. Okay. And F here has force per unit volume units. So now we will use the rigid walled box mode shapes which is phi mnq, okay, x comma y comma z is equal to m pi cos m pi x over Lx into cos n pi y over Ly into cos q pi z over Lz. Okay. And of course the resonance frequency is given by kmnq square, which is omega mnq square by c square, which is m pi by Lx whole squared n pi by Ly whole squared q pi by Lz whole squared. Plus n pi by Ly whole squared plus q pi by Lz whole squared. So that the omega mnq is equal to c square root of m pi by Lx whole squared plus n pi by Ly whole squared plus q pi by Lz whole squared. So if let me draw the picture now at least. We have a box, okay. We have a rectangular box which is rigid walled. So let me say this is my x, so Lx is the dimension, that's my y, so Ly is the dimension, and that is Lz. Okay, that's okay. So now what we are going to do, and there is a source somewhere in here, some source in here which is harmonic. Okay. Now we are going to expand the pressure, okay, let's say P tilde, which is a function of x, y, z and t in terms of the mode shape functions. Okay. These mode shape functions are orthogonal and they have a completeness property. That means within the space they can adequately represent any function p, okay, provided you have a weight that goes along with it, and the more number of modes you take, the better approximation you get for the p. You can get closer and closer to the actual value by taking more and more terms. Okay, so that's the completeness in a very simple form. Okay, and so they make a very good basis. They make a good basis to represent the pressure. Okay. Now if I substitute this into my equation, Helmholtz equation, what do I get? I get del square plus k square summation m n q phi m n q E tilde m n q is now equal to minus q, and the time has disappeared from both sides. Okay, and if I switch the summation and operator, I get summation triple, I will use just one sum mnq del square plus k square phi m n q x y z p tilde m n q is equal to minus q. Okay. This k square is coming from the external excitation, okay, because it is a linear system and we have dropped the initial transient response. So, the final response will be at the excitation frequency. So, this omega decides that k, okay. But now we have del square of phi m and q, okay, and phi m and q we wrote it on the previous page, and del square is del 2 del x square plus del 2 del y square plus del 2 del z square in rectangular Cartesian coordinates. And here we have cos m pi x over Lx, cos n pi y by Ly, cos q pi z over Lz, okay. So, if we do this, what do we get? If we apply this operator on this function, what do I get? I get minus m pi by Lx whole squared into the same cos, okay, the double derivative gets me back to cos except with a minus. So, I get cos, cos and cos. Similarly, the y operator on this twice gives me minus n pi by Ly, again a cos, and similarly the z operator on this. So, I will get minus m pi by Lx whole squared minus n pi by Ly whole squared minus q pi by Lz whole squared. That is what I will get, is del square operating on phi m and q, okay. So, we will give this a name minus k square m and q, okay. And of course, here the phi m and q remained, okay. Let me do this. Phi m and q. Okay. So, the del square operating phi m and q gives me this, and in product phi m and q. So, this is an algebraic expression. This is an algebraic expression, whereas this is the derivative, the partial derivative on phi m and q. So, when phi m and q is a mode shape, this is what you get, this is the advantage you get. The del square operator on the mode shape gives me this, okay. That happens only because this is the mode shape, okay. So, now here del square operating on phi m and q is minus k square m and q phi m and q, okay. So, what happens now? I have the summation, single summation symbol, okay. Del square has operated on phi, so I get minus k square m and q plus k square and phi m and q x comma y comma z p tilde m and q equal to minus q. Here p tilde m and q are unknowns, they are the coefficients which have to be found, okay. So, now we use orthogonality of these modes, orthogonality of mode shapes. Okay. So, if we use that, what we do is we multiply by a mode shape of a different index, k square minus k square mn q phi mn q into, let's say, phi r s t p tilde mn q dv, dx dy dz, and on the right I do the same, okay, and put an integral, volume integral over dx dy dz. So here also a volume integral minus q into phi rst dx dy dz. The orthogonality now demands that m index has to be equal to r, n has to be equal to s, and q has to be equal to t, so that this integral of volume phi mn q phi rst dv is not equal to 0, okay, is equal to some gamma m n q provided m equal to n, m equal to r, n equal to s, and q equal to t, t equal to 0 otherwise. As a result, because r and m index has to be same and we have multiplied by a particular mode shape, so the summation goes away and one of those is picked up, okay. So what now happens is that I have this integral over volume, which is, if I expand 0 to Lx, 0 to Ly, 0 to Lz, minus q phi mn q x y z dx dy dz, that is equal to now gamma mn q k square minus k square mn q dx dy, done on this side, into p tilde mn q, so that the p tilde mn q is equal to, I will write this as minus q mn q, okay. So I have minus q mn q by gamma mn q into k square minus k square mn q, okay, that is my pmnq tilde, okay. So what is the total response? P x comma y comma z comma t, what is the total response? Is the summation over mn q minus q mn q by gamma mn q k square minus k square mn q, this is pm tilde mn q, okay, then phi mn q x comma y comma z e to the power of j omega t, okay, is the total response. Now if I collect this one, or collect both of them. Okay. So this is the excitation frequency, and if it approaches km and q, okay, if k square approaches k square m and q, then this pressure will go to a high value. That is the resonance condition. That is resonance. Okay, and the resonance frequency in radians is given by this. Okay, at this frequency you have the particular wave number is km and q, and therefore you have, when k square matches k square m and q, you get a resonance. Okay. Now in this it appears that pressure goes to infinity, however it does not. We are ignoring damping, so it appears like that. Okay. If damping is appropriately included in the denominator as an extra term here, okay, then this pressure will remain finite when resonance hits. Okay. So that's one level. Now if my q has this form, delta x minus x0, delta y minus y0, delta z minus z0, if it has that form, okay, then what happens to this term over here? To this term over here, okay, the p delta x comma y comma z comma t is given by the triple sum over m and q, and this q m and q will change. It will change to minus phi m and q x0 y0 z0 divided by k square minus k square m and q gamma m and q, then phi m and q x comma y comma z e to the power j omega t. Okay. So everything has remained same, numerator denominator, except this one, whereas earlier it was with respect to a general forcing or a volume velocity source. Here the volume velocity source is at a point, or some point y0 x0 y0 z0, it would change. Now the thing is this, if we employ the Kirchhoff-Helmholtz integral equation for the interior geometry, okay, then what is that? The pressure at a certain point x, y, z is given by the integral of g del p dot n minus p del g dot n ds. Okay. Now in some sense, because q is a delta function, this is the green function. this is the green function inside the rigid walled box. Okay, that's true, right? This is an impulse, this is a spatial impulse, okay, and that's what Q is in this case. Then this is the response to that Q, okay. Then this must be the green function, okay. So now what is special about this green function is that it satisfies all boundary conditions. All boundary conditions. Why is that? Because it is composed of phi m and q, the mode shape. It is an infinite sum over mode shape, but every mode shape satisfies the boundary condition. So the infinite sum also satisfies the boundary condition, and so this green function, new green function, satisfies the boundary condition. Okay. What boundary condition? Del g dot n. Del g dot n on the walls is 0. You know, that is the boundary condition it satisfies. Okay. So now if we look at just this integral now, del p dot n on the rigid walls, del p dot n in the rigid walls, okay, is velocity essentially, okay, normal to the walls, that is equal to 0 because it is rigid walled. It is so on all the 6 walls, okay. So now this del p dot n term is 0 and therefore this term is 0. However, the pressure on the walls is unknown, okay, that is okay. But now del g dot n is also 0 because G is composed of mode shapes and mode shapes satisfy the derivative condition on the walls. So del G dot n is also 0. Okay. So now what is the, how does sound happen? How does sound happen? How does sound happen? Okay. It happens, let me just okay, let me just copy maybe this term. Okay, let me copy this one. Let me copy. Copy. So okay, so this is the green function. This is the new green function G. So if we look at this integral, okay, over the volume, G into a Q which is a function of x0, y0, z0, okay, and dx0, dy0, dz0. So this is the G, right. So if I do that, what happens? I get sigma m n q, then minus integral phi m n q, hold on, integral over the volume G, which is summation m n q minus phi m n q x0 y0 z0 phi m n q x comma y comma z e to the power j omega t e to the power of j omega t divided by k square minus k square m n q gamma m n q into q and dx0 dy0 dz0. In other words, summation m n q minus integral q, which is a function of x0 y0 z0 x0 y0 z0 into phi m n q x0 y0 z0 dx0 dy0 dz0 divided by k square minus k square m n q gamma m n q into phi m n q x comma y comma z e to the power of j omega t. Okay. Earlier what did we do? This integral of the q with a mode shape, we gave this number minus q m n q. Okay. So here we have the same integral, so this is also q m n q. So what do I get? I get summation over m n q minus q m n q into phi m n q x comma y comma z e to the power of j omega t divided by k square minus k square m n q gamma m n q. Okay. So how does this look like? We have just performed this integral. Okay, perform this integral. So now if I compare it with this pressure term that we computed, copy and paste. Okay, minus q m n q phi m n q x y z phi m n q x y z e to the power j omega t e to the power j omega t, and the same denominator. This is indeed p tilde x comma y comma z comma t. So what does it mean? If I know my g due to a delta function, inside the volume as a modal sum, over here, okay, then given any other distribution of sources inside the volume, the response is integral over the volume this g times the q x0 y0 z0 dx0 dy0 dz0, and therefore the new form of the KH integral, the new form of the KH integral equation with a source is P at x, y, z comma t is integral g del p dot n minus p del g dot n over the surface plus an integral over the volume g q dv. Okay. This g has terms which extend from x0, y0, z0, the source points, to x, y, z, the receiver points. Okay. And then q is composed of the source points. Okay. So q is composed of x0, y0, z0. G is composed of response at x, y, z to an input at x0, y0, z0. So this is the form of the KH integral when you add a source term. G is the free space Green function. Now I will just do one more thing here, which is just look at the mode shapes briefly. Okay. Suppose I have a rectangular box with dimensions Lx, Ly and Lz. Okay. And I am just taking some numbers. Let me take Lx equal to 3, Ly equal to 4 and Lz equal to 5 meters. Okay. And I will take c, the speed of sound, to be 300 meters per second as a convenience. Okay. And the f frequency, resonant frequency in hertz is c by twice pi square root of m pi by Lx whole squared plus n pi by Ly whole squared plus q pi by Lz whole squared. I will just take some simple cases and look at resonances and mode shapes. Okay. Now c is 300 and twice pi is about 6. So c by twice pi I will approximate it as 50. Okay. So let us see, I have m index, n index, q index, fm and q in hertz, and I will just look at a shape. Okay. So if it is 0 0 0, then fm and q is 0 because m is 0, n is 0, q is 0, and this is just a rigid body sort of mode, it has no oscillations. Okay. The entire box has one uniform pressure which is not oscillating. Or okay. Now next, suppose we take m is 1, n as 0 and q as 0. Then I have c by twice pi, I said I will take it as 50. Then inside I have m is 1, pi Lx is 3, so pi over 3 is about 1. Okay. So this is equal to 1, so it is 50 hertz, 50 hertz approximately. And how does the mode shape look? In the xz plane, okay, it varies. It starts off with a plus, goes as a minus, because these mode shapes, because of rigid walls, give maximum pressure at the walls. Okay, this is plus and this is minus. Okay, and if we look at the y direction, there is no variation. Along y there is no variation, so this will look like minus all through as you move. Okay. And on the top also you see a minus here, you will see a plus here. Okay, that is your 1 0 0 mode. Okay. Now if I take 1 1 and a 0, I have a 50 outside, I have a square root of pi by 3 whole squared and pi by 4 whole squared. Pi by 3 I will take it as a 1, so I have square root of 50 into square root of 1. Pi by 4 I will take at 0.7, 0.7 squared 0.49, so 0.5, and root of 1.5 I will take as 1.2 because it is 1.44. So this is equal to 50 into 1.2, which is about 60 hertz, let us say. And how does this look like? This mode looks like, along the xz plane I have 1, okay, let us say is a plus, is a minus. Okay, why? This is cos pi x by Lx. Okay, so at x equal to 0 I will have one peak, at x equal to Lx I have the negative peak. Okay, similarly in the other direction now I have a variation. Okay, so I have a plus here and a minus here. Okay, so that what happens is a product. Okay, so this minus and this minus give a minus here. Okay, this minus and this minus give a plus here. Similarly this plus and this plus and this plus give a plus here, and then this plus and this minus give a minus here. Okay, why? We have a product here, cos pi x by Lx, cos pi y by Ly. This product is what we are looking at. Okay, and there is no variation in the z direction. Along the z there is no variation. Okay. And similarly the last case, if I take m, n and q as 1 1 1, okay, then my f, m and q is 50 square root of 1 plus 0.5, let us say, and then pi by 5 I will take that whole squared, I will take that to be 0.4. Okay, so this total is 1.9, I will approximate as 2. So I have 50 root 2, which is approximately 50 into 1.4, which is 70 hertz. So because all three indices are 1, this is like cos pi x by Lx, cos pi y by Ly, cos pi z by Lz. Okay, so if I look at it in the xz plane, x has this behavior, positive and negative, and z also has a similar behavior, it is positive and negative. Okay. So, this positive and this negative will keep it negative. So, we will have now a negative here, this negative and this negative makes it positive, I will have a positive here, this negative and this positive makes a negative here, and so positive here. So, if I erase this part, this is how the combination now looks like. Okay. So, it looks like this. Plus minus plus minus. Now, if I add the y behavior, which is plus here and a minus, so how will the combination look like? Here also z is there. Okay. Now, on this face x and z are taken care of. So, now if I look at this point, this plus which includes x z behavior, this minus will make it a minus, this plus and this plus will make it a plus here, and so a minus and a plus. You can check it if x at its maximum, which is cos pi, okay, which is negative here, and z at its maximum, which is also minus 1. So, x maximum, z maximum, minus 1 you get a plus. Then you combine plus with the y negative, you get a negative. Okay. So, at x equal to Lx, y equal to Ly, z equal to Lz, you have triple minuses, so you get a minus here, and from there you can alternate signs and get this picture. That is how the sound field looks like. If you take a microphone and move around the box inside, this is how you will see it. I close this lecture here now. We will start with the interior cylinder acoustics in the next class. Thank you.